The mid-20th century was defined by a relentless obsession with speed and the belief that human engineering could conquer every physical barrier, including the sound barrier for commercial travel. In the early 1960s, the United States government initiated a high-stakes competition to build the world's most advanced supersonic transport, or SST. The goal was to create a passenger jet that would not only compete with, but utterly dominate the Anglo-French Concorde and the Soviet Tupolev Tu-144. This ambition gave birth to the Lockheed L-2000, a titanium masterpiece designed to carry over 200 passengers at a blistering Mach 3.0. It was a vision of the future where the Atlantic Ocean could be crossed in less than 2 hours, effectively shrinking the planet. The Lockheed L-2000 represented the absolute pinnacle of American aerospace prestige, a project so vast and expensive that its success was considered a matter of national survival in the global technological race. Before we dive into the spectacular collapse of this supersonic titan, please take a moment to hit the like button and subscribe to Never Built. We uncover the lost future that the world canceled. We promise you this. Stick with us until the final segment, and you will learn the one specific, chilling economic calculation that proved the L-2000 would have been bankrupting every airline that flew it, even if every seat was sold for double the price of a standard ticket. Here is why this ultimate symbol of American aviation was abandoned. The first overwhelming obstacle was the titanium thermal crisis. To fly at Mach 3.0, the L-2000 had to be constructed almost entirely of titanium to survive the friction-induced heat that would melt conventional aluminum airframes. This required an entirely new, unproven manufacturing industry. The second, inescapable hurdle was the sonic boom catastrophe. The sheer size and speed of the aircraft generated a sonic boom so powerful it threatened to shatter windows and cause structural damage across entire continents, leading to a total ban on supersonic flight over land. Finally, the project was fatally wounded by the internal competition failure. Despite its superior aerodynamic stability, the L-2000 was forced to compete against the even more complex Boeing 2707 in a government-mandated showdown that drained resources and political will before a single commercial flight ever took place. The engineering challenge of the Lockheed L-2000 began with its radical double-delta wing design. Unlike the simple delta wing of the Concorde, Lockheed proposed a massive fixed-wing configuration that promised exceptional stability at both low speeds for takeoff and extreme supersonic speeds for cruise. This design eliminated the need for complex variable sweep wings, which were the primary downfall of its Boeing competitor. However, the sheer surface area of this wing created immense skin friction. At speeds exceeding 2,000 miles per hour, the airframe would reach temperatures of over 500 degrees Fahrenheit. This necessitated the use of specialized titanium alloys, a material that was notoriously difficult and expensive to machine, weld, and form in the 1960s. The Lockheed plant in Burbank, California, had to develop completely new industrial processes just to handle the exotic metal, leading to astronomical development costs that began to spiral out of control before the first prototype was even half finished. The scale of the L-2000 was intended to provide a decisive economic advantage over its rivals. While the Concorde was restricted to approximately 100 passengers, the L-2000 was designed for a high-density configuration of up to 250 people. This increased capacity was supposed to offset the massive fuel consumption required for Mach 3 flight. However, the weight of the titanium airframe and the massive engines needed to push it through the atmosphere meant that the aircraft had to carry an unprecedented volume of fuel. This created a vicious cycle where more fuel required larger wings and more powerful engines, which in turn required even more fuel. The resulting aircraft was a behemoth of engineering that pushed the limits of existing airport runways and hangars. The cost of upgrading ground infrastructure globally to accommodate the L-2000 added another hidden layer of financial burden that many airlines were increasingly unwilling to bear as the project progressed. Political support for the SST program was initially driven by national prestige, but it quickly eroded under the weight of environmental and fiscal reality. The United States government was essentially subsidizing a luxury transport system for the elite at a time when the nation was facing the immense costs of the Vietnam War and the space race. Opponents in Congress argued that the billions of dollars being poured into Lockheed and Boeing would be better spent on social programs or improving existing subsonic travel. The public perception of the L-2000 shifted from a symbol of the future to an example of government waste. The noise pollution issue became the rallying cry for a growing environmental movement. Protesters pointed out that the sonic boom generated by a Mach 3 aircraft would follow it like a shadow across the country, creating a continuous carpet of noise that would affect millions of citizens. This political pressure eventually led to the 1971 ban on supersonic flight over the continental United States, a decision that instantly destroyed the primary business case for the L-2000 and left Lockheed with an aircraft that could only fly at its top speed over the open ocean. The internal rivalry between Lockheed and Boeing was perhaps the most damaging aspect of the American SST program. The Federal Aviation Administration forced the two companies into a multi-year design competition that was essentially a technological war of attrition. Lockheed focused on a refined, stable, and theoretically buildable design with the L-2000. Boeing, however, proposed the 2707 with swing wings, a much more ambitious and risky configuration. In the end, the government chose the Boeing design, only for Boeing to realize later that the swing wing mechanism was too heavy to be viable. This meant that the L-2000, which many engineers believed was the superior and more realistic aircraft, was discarded in favor of a design that eventually collapsed under its own weight. The loss of the contract was a devastating blow to Lockheed, effectively ending their dreams of supersonic dominance and leaving the American aviation industry with nothing to show for a decade of research and billions of dollars in investment. The L-2000 was the right aircraft at the wrong time, caught in a web of political maneuvering and industrial overreach that proved to be more powerful than its Mach 3 engines. The second phase of the Lockheed L-2000's inevitable decline was centered on the extreme material science limitations that turned the assembly line into a financial graveyard. While the Concorde relied on conventional aluminum alloys, limiting its speed to Mach 2.0 to prevent the airframe from softening due to heat, Lockheed refused to compromise on its Mach 3.0 requirement. This decision forced the engineers into a realm of physics where everything they knew about aviation was obsolete. At Mach 3.0, the friction of the air molecules against the fuselage generates temperatures that would cause aluminum to lose its structural integrity almost instantly. The only solution was titanium. However, in the 1960s, titanium was not a standard industrial commodity. It was an exotic, temperamental metal primarily sourced from the Soviet Union, the very adversary the United States was trying to outpace. The manufacturing nightmare of the L-2000 began with the sheer difficulty of working with this metal. Titanium is notoriously memory-intensive, meaning it resists being bent into the complex curves required for a supersonic fuselage and tends to spring back to its original shape. Lockheed had to invent entirely new hot-forming processes where titanium sheets were pressed into shape at temperatures exceeding 1,000 degrees Fahrenheit in vacuum chambers to prevent the metal from becoming brittle due to oxygen contamination. Every weld on the L-2000 had to be perfect. A single microscopic impurity in a titanium weld could lead to a catastrophic structural failure at 3 times the speed of sound. This level of precision required a specialized workforce and a clean room environment on a scale never before seen in commercial manufacturing. The labor hours required to produce a single L-2000 wing section were 10 times higher than those for a subsonic jet, leading to a production cost that made the aircraft's sticker price a fantasy for even the wealthiest national airlines. Beyond the skin of the aircraft, the internal system's heat sink became an unsolvable paradox. While the titanium exterior could withstand the heat, the sensitive electronics, the hydraulic fluids, and most importantly, the 200 passengers inside, could not. The L-2000 required an environmental control system of unprecedented power. To keep the cabin at a comfortable 70 degrees while the outer skin was glowing at 500 degrees, the aircraft had to use its own massive fuel supply as a primary coolant. The fuel would circulate through heat exchangers before being fed into the engines, absorbing the heat from the cabin and the hydraulic systems. This meant that as the flight progressed and fuel was consumed, the aircraft's ability to cool itself actually decreased. On a long-range flight from New York to London, the thermal management system would be pushed to its absolute breaking point, leaving no margin for error. If the cooling pumps failed for even a few minutes at Mach 3.0, the internal temperatures would skyrocket, potentially cooking the passengers and frying the avionics before the pilot could even decelerate. The aerodynamic stability versus complexity debate was another area where the L-2000 faced internal sabotage. Lockheed's engineers, led by the legendary Kelly Johnson, insisted on a fixed-wing double-delta design. They argued that the complexity of a swing wing, like the one proposed by Boeing, would be its downfall. They were right, but their solution came with its own heavy price. The fixed double-delta wing was optimized for high-speed cruise, which made the aircraft notoriously difficult to handle during the low-speed approach and landing phases. To prevent the L-2000 from stalling as it slowed down to land, it had to maintain a very high angle of attack, with its nose pointed sharply upward. This created a visibility problem so severe that Lockheed had to design a weather vision nose that could drop or droop during landing, similar to the Concorde but much larger. This mechanical complexity, combined with the extreme landing speeds, meant that only a handful of the world's most skilled pilots would ever be capable of landing the L-2000 safely, and only on the longest, most reinforced runways in existence. The global fuel crisis and economic shift of the early 1970s was the final external force that turned the L-2000 into a relic before it ever flew. Supersonic flight is inherently inefficient. The energy required to push a massive airframe through the drag wall at Mach 3.0 is exponentially higher than at subsonic speeds. The L-2000 was designed in an era of cheap, abundant oil. When the geopolitical landscape shifted and fuel prices tripled, the L-2000's fuel consumption became a death sentence for its commercial viability. Airlines that had once clamored for supersonic prestige suddenly realized that a fleet of L-2000s would consume more fuel in a single day than their entire subsonic fleet did in a week. The seat-mile cost, the standard metric for airline profitability, was so high for the L-2000 that a round-trip ticket would have to cost more than a luxury car just for the airline to break even. The dream of the Mach 3.0 future vanished as the reality of the balance sheet took over, proving that even the most beautiful titanium bird could not fly against the wind of economic necessity. The third critical phase in the decline of the Lockheed L-2000 was the insurmountable battle against the sonic boom, a physical phenomenon that turned the aircraft's greatest strength into a social and political weapon used against its existence. While engineers at Lockheed had mastered the aerodynamics of Mach 3.0, they could not rewrite the laws of atmospheric physics. A sonic boom is not a single event that occurs only when an aircraft breaks the sound barrier. It is a continuous pressure carpet that follows the aircraft along its entire supersonic flight path. For an aircraft as massive and fast as the L-2000, this pressure wave was calculated to be significantly more intense than that of the smaller Concorde. The sheer volume of displaced air at triple the speed of sound created a shock wave capable of rattling foundations and shattering glass across a path 50 miles wide. As the project progressed, the public and political outcry regarding these thunderclaps from the sky intensified, leading to a massive grassroots environmental movement that focused specifically on the noise pollution of the American SST program. The strategic incompatibility of the L-2000 soon became apparent as international aviation authorities began to draft restrictive legislation. The United States Federal Aviation Administration was forced to consider a total ban on supersonic flight over land, a move that would fundamentally destroy the aircraft's mission profile. The L-2000 was designed for transcontinental and transoceanic speed. If it was forced to fly at subsonic speeds until it reached the coastline, it would spend a massive portion of its flight operating at its most inefficient regime. In subsonic flight, the massive double-delta wing and high bypass engines were incredibly fuel-hungry compared to a standard Boeing 747. This meant that on a flight from New York to Los Angeles, the L-2000 would offer almost no time savings while costing 10 times more to operate. This logistical reality caused major domestic carriers like TWA and Pan Am to reconsider their orders, realizing that a Mach 3.0 jet that was legally prohibited from flying at Mach 3.0 over the United States was a multi-billion-dollar liability. The internal testing failures and the results of the Oklahoma City sonic boom tests provided the final scientific evidence that the L-2000 could not coexist with civilian populations. In a government-led experiment, supersonic jets were flown repeatedly over Oklahoma City to gauge public reaction and physical damage to buildings. The results were catastrophic for the SST program. The constant booming led to thousands of damage claims and widespread psychological distress among residents. These tests proved that no matter how sleek or advanced the L-2000 was, its wake was too destructive for a modern populated continent. Lockheed attempted to design specialized, low-boom flight profiles, but these required such a significant reduction in speed and altitude that they nullified the aircraft's primary technological advantage. The physics of the atmosphere had effectively placed a ceiling on the American dream of supersonic travel, and the L-2000 was the first victim of this invisible barrier. The titanium supply chain vulnerability also introduced a chilling geopolitical paradox that threatened the project's long-term viability. Because the United States lacked sufficient domestic titanium reserves to build a fleet of hundreds of L-2000s, the aerospace industry was forced to secretly procure the metal from the Soviet Union. This meant that the very nation the United States was trying to surpass in the Cold War was the primary supplier of the material needed for its most advanced prestige project. The CIA had to set up elaborate front companies to purchase Soviet titanium, which was then funneled to Lockheed. This created a massive national security risk. If the Soviets had realized the true destination of the titanium, they could have cut off the supply at any moment, instantly grounding the entire L-2000 production line. This reliance on a hostile foreign power for a strategic defense-adjacent project made the Nixon administration increasingly nervous, contributing to the eventual withdrawal of federal funding. The logistical burden of airport infrastructure became the final hidden cost that turned airport authorities against the L-2000. Due to its extreme landing speeds and the heat of its engines, the L-2000 required runways that were not only longer than average, but also constructed with heat-resistant concrete. Standard asphalt would soften under the exhaust of the L-2000's 4 massive engines during taxiing and takeoff. Furthermore, the aircraft's unique nose-high landing attitude necessitated completely new passenger boarding bridges that could reach the elevated cabin height. The cost for a single international airport to upgrade its facilities to accommodate the L-2000 was estimated in the hundreds of millions of dollars. As fuel prices continued to rise and the public became more hostile toward the project, airport managers were unwilling to commit to these expensive modifications for an aircraft that appeared increasingly likely to be banned from their airspace. Finally, the internal morale collapse at Lockheed as they lost the FAA competition to Boeing in 1966 marked the beginning of the end. Although the L-2000 was widely considered the more aerodynamically sound and realistic design, the government chose the Boeing 2707 because of its larger capacity and more ambitious, though eventually failed, swing-wing technology. This decision left the Lockheed engineering team, which had dedicated years to the L-2000, in a state of professional devastation. While they were encouraged to keep the project on standby in case Boeing failed, the momentum was lost. The brightest minds at Lockheed's Skunk Works began to move on to other classified military projects, leaving the L-2000 to gather dust as a series of wooden mock-ups and unfinished blueprints. The dream of the Mach 3.0 passenger jet was dying not from a lack of engineering brilliance, but from a fatal combination of bad timing, political maneuvering, and the unyielding laws of acoustics. The fourth and final phase of the Lockheed L-2000's history is the legacy of its abandonment, a decision that fundamentally solidified the future direction of commercial aviation and marked the end of the speed over everything era. The cancellation of the American SST program in 1971 was not just a blow to Lockheed. It was a definitive signal that the aviation industry would pivot toward efficiency, capacity, and environmental sustainability rather than the pursuit of Mach 3.0 prestige. The financial and environmental lessons learned from the L-2000's failure became the bedrock of the modern wide-body era, leading directly to the dominance of the Boeing 747 and the focus on subsonic, high-capacity travel. The U.S. government's decision to withdraw funding for the SST program led to an immediate and painful reevaluation of national technological priorities. The billions of dollars already spent on the L-2000 and the Boeing 2707 were written off as a massive sunk cost, sparking intense debates in Congress about the limits of government intervention in private industry. This failure ensured that for the next half-century, no major American aerospace firm would attempt to build a supersonic passenger jet with public money. The strategic focus shifted from reaching London in 2 hours to moving 500 people across the Atlantic at the lowest possible cost per seat. The L-2000 was the last gasp of the glamorous, high-risk aerospace culture that had defined the 1950s and 60s, a culture that was ultimately grounded by the cold, hard mathematics of airline profitability. The aerodynamic and material science research conducted for the L-2000 did not entirely vanish, however. The advancements Lockheed made in large-scale titanium fabrication and high-temperature thermal management systems were eventually funneled into classified military programs. The techniques developed at the Skunk Works for the L-2000's airframe directly influenced the construction of high-speed reconnaissance aircraft and advanced strike fighters. The L-2000 was a commercial failure, but it served as a massive, unintended laboratory for the next generation of military aviation, proving that even a failed project can provide the technological DNA for future success. The double delta wing research, in particular, provided invaluable data on vortex lift and high alpha stability that would eventually be used in the design of the space shuttle and other delta wing platforms. The environmental legacy of the L-2000's cancellation cannot be overstated. The public battle over the sonic boom and ozone depletion concerns, which were widely debated at the time, established the first major environmental hurdles for the aerospace industry. The 1971 ban on supersonic flight over land remains one of the most significant pieces of aviation legislation in history, acting as a permanent barrier that has prevented the resurgence of supersonic travel for decades. Every modern startup attempting to revive the SST dream must still solve the sonic boom problem that the L-2000 could not overcome. The L-2000 was the project that taught the world that the sky has limits and that technological progress must be balanced against the quality of life on the ground. Furthermore, the economic shockwaves of the project's end led to a massive consolidation within the American aerospace sector. Thousands of highly specialized engineers and technicians who had worked on the L-2000 were suddenly unemployed, leading to a brain drain that affected the industry for years. The Lockheed Corporation itself faced severe financial distress following the loss of the SST contract and other setbacks, eventually requiring a controversial government-guaranteed loan to survive. This era of aerospace instability proved that relying on massive, high-risk government-funded projects was a dangerous business model, leading to the more diversified and commercially focused aerospace giants we see today. The L-2000 was the project that taught the industry that even too big to fail technology can crash when the market reality shifts. The L-2000 remains a magnificent conceptual monument to the ambition of the space age. It was a project defeated by the convergence of physics, economics, and a changing social conscience. The American SST was not a technical impossibility. It was a commercial and environmental absurdity. The decision to ground the L-2000 was the definitive moment the world realized that the future of travel lay in the comfort of the masses, not the speed of the few. The titanium bird was designed to outfly the sun, but it was eventually brought down by the weight of its own fuel tank and the sound of its own wake. The ultimate fate of the Lockheed L-2000 lies in the museum of what might have been, a testament to the fact that in the world of mega projects, the fastest path is often the one that leads directly to a dead end. The L-2000 was the pinnacle of American engineering, a Mach 3.0 dream that was simply too fast for the world it was meant to serve. The final question remains: the L-2000 failed primarily because of the sonic boom and extreme fuel costs. Today, new companies are developing quiet supersonic technology and sustainable aviation fuels. Do you believe that these technological breakthroughs will finally allow a successor to the L-2000 to succeed? Or has the era of high-speed passenger travel been permanently replaced by the efficiency of the subsonic wide-body jet? Join the discussion below and tell us. If you could fly anywhere in the world in 2 hours, but the ticket cost $20,000, would you take the flight? If you enjoyed this professional deep dive into the abandoned engineering of the Lockheed L-2000 supersonic transport, like this video, and subscribe to the channel for more stories about the incredible projects that were never built.